Hello everyone, welcome to another ME 296 lecture. This time we're going to do a brief and not very mathematically rigorous breakdown of why we're going to use the techniques of differential operators and the Laplace transform in the class. We're going to lean more heavily on the Laplace transform because it is the industry standard, but it is very common to the differential operator and you will be expected to know how to use those as well. So these techniques are very commonly used to solve different kinds of differential equations, and differential equations can certainly be used to describe circuits. We'll get more into that on another lecture coming up soon. So the reason these are used, in the most general of terms, is that they change calculus into algebra. So with that, let's get started with differential operators. We define a differential operator as equal to the derivative of some function, and the notation makes it clear that the act of taking a derivative is separate from the function we are examining. And by making this distinction, we can develop several properties that are extremely useful. So notice up at the top that our operator d is just equal to d over dq, where q is a variable we're taking the derivative of. It says nothing about the form of the function. And that's what I mean by making the derivative separate from the function. So the first important property that comes from making this distinction is our ability to distribute the operator. The second is the ability to multiply the operator. And the third allows us to solve combinations of exponentials and polynomials. There are lots of other properties, but these three are the most relevant to circuit analysis, and they're the ones we'll be using in the class. So one additional thing that we need is called the exponential input theorem, which tells us how we can find the solution of a differential equation where our driving function is some kind of exponential input, where our driving function is the part that all of our differentials are equal to, such as y prime is equal to f of x would be the driving function. A lot of times it's 0, so we would just have y prime is equal to 0, which I guess would be a pretty easy one to solve, but in that case our driving function would be 0. And we like the exponential input theorem especially because this comes up all the time in circuit analysis. Just think of the discharge curve of a capacitor. Isn't that an exponential? So if our input to a circuit is some kind of battery or capacitor that starts fully charged and that charge goes into the circuit, well, that's an exponential input. And also the Fourier transform tells us that any function can be described as a sum of exponential functions or trigonometric functions, but exponential and trigonometric are really the same thing. So this generalizes the theorem to anything we're likely to see in this class. So the exponential input theorem tells us that if we define p of d as a polynomial function of degree s with constant coefficients, where our variable is the differential operator d, then the solution of a differential equation with exponential input has the form y equals x to the s times e to the ax over a. And this comes up a whole lot. So from that theorem and from some of the properties, we can generalize solutions of the form d plus a, that quantity, times y. We can generalize the solution as y is equal to some constant c times e to the negative ax, which also comes up a whole bunch. So because this isn't mathematically rigorous, I'm not going to prove any of these. They are true, and there are lots of websites and other places that you can find them, not the least of which is your math class. So with that, let's just do a pair of examples so we can see how and why we use them this way. So let's start with using differential operators to find the derivation of a function. We're going to take the third derivative of e to the negative x times sine of x, which if we do this by hand using regular differential problems, this turns into a big nasty problem. But if we use differential operators instead and use our properties and rules, it becomes much simpler to solve. So first, let's substitute our differential operator d for d of x, and because it is the third derivative, it becomes d cubed times e to the negative x times sine of x. So we're going to use our third rule to obtain e to the minus x times d minus 1 to the third times sine of x. And then we can expand this because we have d minus 1 to the third, we can expand this to a polynomial of degree 3 times the sine of x. So once we do that, all we need to do now is multiply our sine of x through our polynomial and then revert back to the derivations. So this would be something like d to the third sine of x minus 3d squared sine of x plus 3d sine of x minus 1 sine of x. And then we take the derivative. So the first term would turn into the third derivative of sine, which is negative cosine. The second term is the 3 times the second derivative of sine, which is sine again, once we take into account the minus there. The third term just becomes 3 cosine, and the final term becomes minus sine of x. So we're done. We have e to the x times the quantity 2 cosine plus 2 sine after we take care of the addition and subtraction in there. That was much simpler than going through and actually doing a derivation by hand by taking advantage of these rules and properties. So let's look at how we can use this to solve a differential equation, hopefully equally much more simply than we would otherwise. So we're going to solve the differential equation y double prime plus 4y prime plus 4y equals e to the negative 2x. So first step, sub in the operators. Well, this looks exactly like an example of the exponential input theorem where s is equal to 2. So we're basically done. All we do is we look at our exponential input theorem and we substitute values where appropriate, and we find out that in this case, y is equal to x squared times e to the minus 2x over 2. That was pretty simple. All we did was we transformed our differentiation into differential operators, manipulated them algebraically, and then we were able to see the forms of our final solution right off the bat just by using these. So this is incredibly useful, and it does come up sometimes, especially when doing slightly simpler behavior of circuits. But in the electrical engineering world, the Laplace transforms are the industry standard method of dealing with circuit analysis. So let's start talking about those. So the Laplace transform is defined as taking the integral from 0 to infinity of e to the negative s times our function. And this gives us our function in the Laplace domain, which is different from the original domain. In circuit analysis, our original domain is often time. And then when we take the Laplace transform, we're in the Laplace domain where our variable is s, and this is often taken to be the complex frequency domain. We're not going to worry about that too much in this class, but it does come up quite a bit in more advanced circuit analysis and electrical engineering classes. So just keep that in mind that we're talking about the frequency domain when we're talking about the Laplace transform. So the reason we do this transform is that it gives us super useful properties in terms of integrals and derivatives of our function. Derivatives turn into a factor of s times the original equation, where our original equation is now in the Laplace domain. The second derivative is s squared times our function minus s times our function, and then you have some terms for initial conditions. And then you can continue this on all the way down until you want to stop taking derivatives. Conversely, integrals turn into factors of 1 over s. So if you're taking the Laplace transform of the integral of some function, you get 1 over s times the Laplace transform of that function. And you can see how you might be able to chain this into third integrals, fourth integrals, and so on. I'm not going to prove these, but you will in one of your homework assignments coming up. But for right now, let's just accept these as true. For the most part, it's pretty acceptable just to use tables to determine the Laplace transform. You don't need to do it by hand every time. They're pretty well known. And you can also use these tables to revert back into our original time domain once we've already manipulated our circuit the way we want to. So just as an example, let's say we have this complicated circuit, we turn it into Laplace, and then we find that our current, after a whole bunch of manipulation, is simply equal to 1 over s in the Laplace domain. If you want to know what that looks like in time, well, we can just use our Laplace lookup table and see that 1 over s is equal to a constant in the time domain. So we just turn it back into a constant. We're done. We don't have to do any integration or derivation to get it back, because reversing the Laplace transform by hand is a pretty tricky integral involving several steps. So I think the best thing to do here is to start doing examples because there are some tricky bits that only really come up with working problems. So let's just do that. We're going to solve using Laplace transforms the differential equation 2y double prime plus 3y prime minus 2y is equal to t times the exponential of negative 2t. So we're going to set our initial conditions to 0, so we don't have to worry about any of those. And the first thing we're going to do, we're going to sub in our Laplace transforms. Our second derivative of y becomes s squared y minus sy. Our first derivative of y just becomes sy. Y becomes y, except now we're in the s domain, so technically y is now a function of s instead of t, but I'm dropping that notation now just for simplicity. And then we take the Laplace transform of our driving function, where our driving function is t times e to the negative 2t. If we look into our Laplace transform table, we find that this is equal to 1 over s plus 2 quantity squared. Now we can factor out the y on the one side and then solve for y such that it's alone all on its lonesome on one side. And then this gives us a pretty nasty looking fraction that is not inside of our Laplace transform table. But if we were able to make this into a series of simpler fractions that are in our table, then our work would be much more simple. So luckily, we're able to do this if we remember how to use partial fraction decomposition to obtain these simpler fractions. And in case you don't remember how, I'm going to work through how to do that real quick. The first step is to factor our denominator. And in our case right now, we get 4 factors. We get one factor of 2s minus 1. And then we have s plus 2 squared, and s plus 2 cubed. Because when we factor our original thing, we have s plus 2 squared in our initial fraction from our driving function. And then when we factor our second fraction, we get 2s minus 1, and then another factor of s plus 2 for a total of s plus 2 cubed. And when doing partial fraction decomposition, we need to make sure we include one fraction of each power of our factors. So the next step after doing this is to set our original fraction equal to the sum of our 4 factors as fractions, with our numerators being unknown variables. So now that we've done that, we have our original fraction times a over 2s minus 1 plus b over s plus 2 plus c over s plus 2 squared plus d over s plus 2 cubed. Now how do we solve for our unknowns? First thing, multiply through. So we take our original denominator and we multiply all the way through, so we wind up with 1 is equal to big long function. The next step is to take our roots to simplify this big long function. Our roots in this case are s is equal to negative 2 from the s plus 2 factors and 0.5 from the factor of 2s minus 1. So first, let's use the s minus equals minus 2 and substitute that in for s. This greatly simplifies everything. We wind up with 1 is just equal to d times the quantity 2 times negative 2 minus 1. Because in all the other parts of our equation, we have factors of s plus 2, which when we substitute in negative 2 for s becomes 0, so they all drop out. And now we have trivially discovered that our unknown d is equal to negative 0.2. Now we use our second root, s equals 0.5. In a similar vein to our first root, we find out that 1 is equal to a times the quantity 2 times 0.5 plus 2. And this is just as easy, cubed. And this is just as easy to solve for as d, and we find that a is equal to 0.064. So now we have 2 of our unknowns solved for with 2 of our roots. We have no more roots, unfortunately, but we have already solved for 2 of our equations. So now our next step is to go back and factor our original big long function. So you would factor, multiply through s plus 2 cubed times a, b times the quantity s plus 2 squared times 2s minus 1, get that into a big long equation, and then gather together all variables that are attached to a power of s to the third, all variables that are attached to s squared, and so on and so forth, and then build a system of equations around that. So on the left-hand side, we have no powers of s to the third. So all the variables attached to s plus 3 are equal to 0. So we wind up with a plus 2b equals to 0, and so on down the line until we wind up with our set of 4 equations and 4 unknowns, even though we really have solved for 2 of them already. Now, I'm not going to go through and show exactly how to expand all this, but it should be pretty simple to do for everyone. So we have our first equation, a plus 2b equals 0. We know a, we don't know b, so this turns into a pretty trivial equation, 0.064 plus 2b equals 0, b is equal to minus 0.032. We march down to the second one, because now we know a and b, we need to know c. We find that the equation is equivalent to 6 times 0.064 plus 7 times negative 0.032 plus 2c equals to 0. Go through all that, and you get c is equal to minus 0.08. So now we have all 4 of our unknowns as knowns now, and it's best practice to go through and make sure that our system is consistent with all 4 of our equations. I didn't show that here in the interest of space, but if you were doing this on an assignment or an exam, I would absolutely expect that you go through and you show that all of our variables satisfy all 4 of the equations that are shown here, which should not be too difficult to do. Just be aware that I expect you to do it on an assignment. Okay, so now we have our 4 unknowns that we can now substitute into our original fractions. So we wind up with y in the Laplace domain is equal to 0.032 times the quantity 1 over s minus 0.05, where I have gotten s by itself by dividing through by 2 on the entire term, just so that s is by itself, because remember in our Laplace transform table, s is always by itself. We have no like as squared or whatever in there, at least in the denominator. And then our second term becomes minus 0.032 times 1 over s plus 2, and then minus 0.081 over s plus 2 squared, etc. So now these are in forms that are, in fact, on our lookup table, so we can use that to go through and go back to our original time domain. So we do that. And now we have our final equation. That was much simpler than going through and trying different random equations to see if they work, or hoping that we've seen something similar to this before. The only hard part was going through the partial fraction decomposition, but that's just algebra, and we should all know how to do algebra by now. Well, this wasn't too mathematically rigorous, but I hope that it was kind of helpful in seeing why we would want to use these techniques and where they come from, at least a little bit. Overall, they're very helpful in solving complicated differential equations because we stop having to do calculus and just do algebra instead. And all we need for algebra is a little patience and a lot of paper. And trust me, complicated differential equations come up all the time in circuit analysis, and having tools like this at our disposal greatly simplify our time and the difficulty of the problem, which is very helpful. All right, well, that's all for now. Thanks for listening.